So thank you for the introduction. Thank you very much for Alex and Frédéric for the organization of this colloquium or workshop. When I received an invitation, I was very happy to accept it right away and send you a title on QKD and in particular in device independent QKD. And then I realized that the colloquium was mostly on quantum computing. So I decided to keep the title, but to slightly change the content, admittedly. Sorry for this. And then there will be two parts in my talk. A first part related to Shor algorithm. And in particular, I would like to show you the result of an analysis aiming to quantify quite accurately the resource that we need to perform Shor algorithm. And then comes the second part of my talk, the part that I initially had in mind, which will be a bit squeezed, at least with respect to what I had in mind initially, which will be about quantum key distribution. And in particular, I'll present protocol, the advanced protocol of QKD, which are called device independent. The aim is to try to reduce the number of assumptions that you have in standard QKD, while still providing provable security guarantees. So let's start with the first section on the Shor algorithm. I know that Frédéric made a detailed lecture on Shor algorithm, but let me remind a few points about this algorithm. So it solves a problem that is called the factorization problem, a problem that is easy to understand. I basically take two large prime numbers, P and Q. I multiply them together, get an integer n, a large integer n. I give it to you, and the game is you have to give me back P and Q. So, for example, if I give you 15, you give me back 3 and 5, and you win the game. So this is a simple problem, at least to explain, but it's hard to solve. And in particular, there is no known algorithm that can solve this problem in a number of steps that is a polynomial in the number of bits that I need to write down the integer n. And Peter Shor found an algorithm that can do that efficiently in the number of steps that scales as log n at the power 3. Okay. So this is the starting point. And it's clearly interesting for a quantum physicist, but it can also be seen as a threat for communication security, because it turns out that the factorization problem is used at, you can say it's at a core of a classical crypto system that is called RSA. RSA is widely used. And the consequence of Shor algorithm is that RSA is not secure anymore once a quantum computer is available. So the question is, at least one possible question at this point is, how long will it take before we can really hack RSA with a quantum computer? Or a related question is, what is exactly the resource that is needed to run Shor's algorithm? So let's have a quick look at the Shor algorithm steps. So there are essentially 4 steps. The first step is a step where you choose an integer at random. Then you compute the greatest common denominator between g and n. Most of the time you'll get 1. And then you go to step 3, where you need to compute the period of a function that I call fx, which is essentially the modular exponentiation g at the power x mod n for all possible x, say between 0 and n. Okay? And then again, it's very likely that the period is even, and in this case, you compute the greatest common denominator between g at the power r over 2 minus 1 and n, and this will give you one of the prime number that you are looking for, and obviously you can deduce the other one easily. Okay? So all these steps are nice and easy to do, even classically, except the step 3, because again, we're considering a very large number of possible value for x, And even if it's easy to compute g at the power x, if the number of x is large, then it starts to be complicated. Okay? But this is where comes the trick from Peter Shor. The trick is quite simple. It uses the superposition principle. As we all know, there is a special gate in quantum computing, like Hadamard gates. If you apply Hadamard gates on all the qubits of a given register, then it basically put this register in a superposition of all possible classical value from, say, 0 to 2 to the power k, where k is the number of qubits in your register. And therefore, this means that if you now compute 1 times g at the power x while putting your register in a superposition of all possible value of x you're interested in, this means that by simply computing once g at the power x, you get all possible value of g at the power x for, say, all possible value of x in a superposition. Okay. This is good, but this is not what we want. We don't want the value of g at the power x for all possible value of x. We want the period. And this is, it's possible to get the period using the Fourier transform. So the basic idea is that, you have the classical register x, the register encoding fx. You do apply Fourier transform on the first register, and then measure this first register. You get one of the Fourier component, L, from which you deduce the period. And, well, it can be seen as, a trick where the Fourier transform benefit from an interference of the probability amplitudes that helps you to find the desired period. Okay, so now regarding the complexity, as we were saying before, we can essentially forget the complexity of the Fourier transform. It's a classical essentially a classical Fourier transform. So the resource is negligible, but what is essentially costly is the computation of this modular exponentiation. It essentially takes 2 registers of size n. So it takes a register of size order n. I did not write down the prefactor. The prefactor is in between 2 and 3, depending on the detail of the algorithm itself, the way you really implement it. Where small n is now the number of bits that I need to encode big N. And regarding the number of operations, it scales like n cubed. You can see it because to compute the modular exponentiation, you basically need n multiplication, and each multiplication is implemented with n addition, and each addition requires essentially n elementary operation. So the complexity goes like n cubed, and now everything is clear. You can not only find out about the complexity, but really find out about the detail, gates by gate. And if you do that, then you can compute the expected time, the average time it takes for Shor algorithm to converge as a function of small n. This is the result. Where, of course, I need to consider a time scale for the time it takes to perform one operation. We here assume that it takes 1 microsecond. And I also need to include the error per gate, and this is the quantity that I call P. And by changing P, I get several curves corresponding to several expectation value. And what we conclude from that is that the success probability essentially goes like 1 minus p, which is the probability of performing successfully a given gate, at the power n cubed, which is, again, the number of operations in Shor algorithm. So this basically shows that p has to be small enough as compared to 1 over n cubed. And if you look at the, say, regime where it becomes hard to perform the factorization classically, say in the regime in between 100 and 1,000, you realize that this is only possible provided that you have an error per gate of the order of 10 to the minus 10. So this is the point where you realize that error correction is needed. Error correction is good in the sense that it reduces exponentially the error per gate with an argument that is essentially the depth of the code. The depth is simply the number of operations that are needed to go from one code word to another code word. And now the previous condition is a condition essentially on the depth of your code, and the depth has to be at least of the order of log n cube. Okay? So now if you ask me what is now the cost of Shor algorithm by considering the need for an error correction code, and if we say we're considering the most familiar the error correction code, the surface code, then in this case, the number of physical bits that you need for having a distance d scale like d squared, which means that you need a register which involves a number of qubits that is n times log n cubed, the square of log n cubed. Okay. Now, again, we can be even more accurate in the estimation by now considering a plausible physical assumption for a large-scale processor with given technology. And in particular, if you consider 2D grid of superconducting qubits, then in this case, the connectivity is low. You can only connect neighboring qubits. It's quite reasonable to consider gate error of the order of 10 to the minus 3. We can consider, again, the surface code and consider a cycle time of 1 microsecond, which is basically the time it takes not only to perform a gate, but also to measure the stabilizer associated, say, to one step of the error correction that you need after applying each gate. And then you consider the use of CCZ factories for implementing the non-Clifford operation that are needed to get a universal set of gates, and the trick of using teleportation from this factory to implement Control-Z operation. So with this assumption, it has been estimated by Guitney and Ekera a few years ago from now, but the paper was only recently published in Quantum, that it would take essentially 8 hours to factor 2048 RSA integer with a 2D grid made with 20 million qubits. So it's interesting to consider that, in this 20 million qubits, there are essentially 4 million qubits that are used for producing the CZ, the 30 CZZ factory that are again needed for performing the non-Clifford operation. So one of the author was recently showing that you can even reduce this runtime by adding parallelizations by further parallelization of some of the steps in the addition. This is good, but of course these come at the price of increasing the number of qubits that are needed for having the CCZ factory. Simply because you now want possibly to apply many non-Clifford operations at the same time, and of course for this you need the CCZ state to be available simultaneously. And as you see here, the number of physical qubits that you need per factory is quite large. And this means that if you start doing more and more parallelization, then it's going to be very costly in terms of qubit number. So this means that it might make sense to focus on implementation where that are, say, essentially mostly sequential. And if this is the case, then it might be worse to look at what you gain if you have a quantum memory in addition to your processor. Simply because in this case, you know, gates are applied one after the other. It means that at each step, essentially all the qubits are unused and processed. So it might be worth using a quantum memory to store essentially all the qubits, and this might be a way to very significantly reduce the qubit number in the processor. Okay. So this is what we studied recently with Elie Gaussien. And what we did first is to consider essentially the same assumption and the same physical device that I was showing you before. But now, instead of having a large processor, I have a processor that can be used to produce, or that can implement one CCZ factory and a few logical qubits, exactly 3 logical qubits. And then I use quantum memory, a faithful and multimode memory, to store all the other qubits. If you do that, and again, keep focusing on the same assumption as before, so gate error of the order of 10 to the minus 3. Now we need to keep in mind that this 10 to the minus 3 also include the storage and readout from the memory, and a surface code cycle time of 1 microsecond. That what we found is that it would take 68 days to factor a 2048 RSA integer, with now a processor involving 184,000 qubits instead of 20 millions, provided that you have a memory that can store 5 million qubits. So what I'd like to mention at this point is that, again, this, most of the qubits are used for implementing the CCZ factory. Okay, so the question at this point, if you really want to push the logic, at an extreme point, when you want to reduce more and more the number of qubits in the processor, then what you need to do is to use another code, a code that do not requires the use of this factory to really, reduce the number of physical qubits in the processor further and further. And this is what we did. So we now took 3D gauge color code. This is a code that basically admits, or you can see it as a combination of 2 codes. One code for which you can implement in a transverse and error-corrected way CNOT and Adama gates, and another code where you can implement non-Clifford T gates in transverse and error-corrected way. And the 3D gauge color code is essentially a way to basically switch between these 2 codes. And now this is what logical would look like. It's a 3D code, so you now need, for getting a depth D, you need a number of physical qubit per logical qubit that goes like D cube. And what we could envision, for example, is a quantum memory that can store this many logical qubits in a way that you store the qubit in the same slice to different spatial mode in your memory, and for qubits belonging to different slice, you would use temporal modes. Okay? And now, the good point is that we've shown that you can process this qubit slice by slice. So this means that now you can basically reduce the number of qubits in the processor to a number of physical qubits corresponding essentially to 2 slices of one logical qubit. And if you do that, then it becomes very hard, of course, to do any parallelization. So it now takes a bit more than 170 days for factoring a 2048 RSA integer, but you can do it with a processor involving 13,000 physical qubits. This comes at the price of having a good quantum memory that can store 20 million spatial modes, as well as 45 temporal modes, with a storage time exceeding 2 hours. So let me emphasize that we did not try to optimize the number of modes that needs to be stored in the memory. This is the first point. And the second point is that we should not be worried too much about this 2-hour storage time, because you can eventually release all the qubits from time to time that are stored in the memory and use error correction, to protect them from the decoherence into the memory. And we estimated that it would take about 1 second to do that, to release all the qubits, to correct them with such a processor, and to map them back into the memory. So what this means is that in this case, you only need a storage time exceeding 1 second, at the price of increasing the runtime by about 20%, something fairly reasonable. Okay. So it's now time to go to the second part of my talk. Maybe the take-home message of this part is that with current approach for implementing a quantum computer, you have a challenge, an engineering challenge, aiming to solve the problem of having 20 million qubits on the same chip, cool them down to, say, 10 millikelvin, and make sure that you can address them individually. What we now have is a challenge, a physical challenge, aiming to provide a protocol so that we can store millions of modes in a quantum memory and store them faithfully for a period of time of the order of 1 second. Okay? So somehow we can say, I think fairly, that we turn an engineering problem into a physics problem. Now, let's go to the second part of the talk related to quantum key distribution. Let me try to make a bridge between these two sections by saying that, okay, we have, I think, quite accurate estimate of what it takes to run Shor algorithm. I'll let you decide whether we'll be able to run it in 5, 10, or 15 years. At the time it will take to basically get the resource I was showing you before. But the point to keep in mind is that if you're using today crypto systems that are based on RSA, then what we're saying here is that in maybe 5, 10, or 15 years, the message that we're using or encrypting today with RSA will be known basically, and it's nice to see or to observe that a technology that is not yet there, talking about a quantum computer, is already a threat for today's communication security. So, of course, we have several solutions to this threat. You can focus on other classical crypto systems, but if you want to have a provable security that does not depend on conjecture, basically, then you can use quantum key distribution. And of course, quantum gate distribution is not unconditionally secure. You have essentially three conditions in quantum key distribution. The first one is quantum theory is correct. I don't want to comment on this point. The second one is that the two protagonists that want to get a key, Alice and Bob, they need to be able to exchange messages authentically without the possibility for Eve to alter this messages. Well, let me mention that this is somehow another primitive of cryptography, and you really need it in quantum key distribution, but we know probably secure authentication scheme. And the third point is a point that I would like to comment a bit more, which is the need to trust in the device that Alice and Bob are using for distributing a key. And the trust here goes quite far in the sense that in BB84 protocol, for example, Alice and Bob, they really need to make sure that they know exactly what is the measurement settings that they are using for getting the key. They know exactly the Hilbert space dimension that is relevant for the particles that are produced by the source and things like this. And it's interesting to see whether we can try to get rid of these assumptions and eventually make possible the use of QKD even with devices that are largely unknown. Okay? So the third point I was mentioning before is now replaced by three well-defined points, such that, for example, that that Alice and Bob can process the information in a way that the information remains in the lab, for example. Of course, it won't be possible to get anything secret if this is not satisfied. They also have a device, and with this device, you can sit in your lab as a measurement device with measurement settings and measurement outcomes, but we treat them as black boxes. So instead of measurement settings, we now have the input, and instead of measurement outcomes, we now have outputs. And what we need is that the input to the device, they can be chosen independently from all other devices. All right? And the third condition is that you can also do the post-processing that are needed, error correction and privacy amplification in QKD with trusted computers. But now we'd like to remove the assumption I was mentioning before. I don't know what is exactly the measurement that is performed by Alice box. I don't know exactly what is the Hilbert space dimension associated to the source, but still I would like to prove that I can use these devices to get a key. So let me quickly describe how a device-independent protocol works. You have a number of steps. Alice is here on the left, Bob on the right. And Alice can choose between three inputs. She has a black box, as we saw before, and the black box has three possible questions that I call 0, 1, 2. Bob has a similar box, but with two questions, 1 and 2. And the question 1 and 2 will be used to try to bound the eavesdropper information, while the input 0 of Alice will be such that the results are correlated to the result of the input 1 of Bob. This is called the key generation settings, while the other ones are the test settings. So now what is needed in step 3 is to compute the value of what is called a CHSH core. You can see seen it as a sum of expectation values If I take the expectation value A1, B1, this is simply the probability that the results are the same, given this question 1 and 1, minus the probability that the results are different, given the same input, the same question. Now you end up the protocol with the standard post-processing, error correction, and privacy amplification. And you get a key rate, which is essentially given by these classical processing steps. Privacy amplification is usually based on an extractor. An extractor is essentially a classical operation. You give an input bit string where age quantify the randomness of each bit, and you get a shorter string, but with full uncertainty. The length is reduced, and the reduction is basically given in the most favorable scenario by the entropy of your bit string. Okay. In this case, we're talking about the entropy of the reference key with respect to Eve. And then the error correction is also something fully classical. It requires essentially hash function. The results are hashed and sent from Bob to Alice, and the length of this hash is typically given by the entropy of the reference key with respect to Alice this time. Okay. So the most difficult part in QKD is to quantify properly this quantity, the uncertainty that Eve has on the reference key. And it has been shown that you can quantify this quantity by using the CHSH core that is computed in step 3. This has been shown among other in this paper. And as you see, the function, the lower bound is 1 minus the function of S, where the function is given here, and H is the binary entropy. Okay. Good. This is good, because now, in this, in the way you compute the CHSH quantity, you don't need to assume that you know exactly what are the measurement device. You don't need to assume what's the Hilbert space dimension. It's just the quantity that you get access directly from the measurement outcome. Okay. So we say that this protocol guarantees security in a device-independent way, without the need to know the detail of the functioning of the measurement and of the source. Now, this is an advanced QKD scheme, but it turns out that so far there is no experimental demonstration of device-independent QKD. And we're interested to try to provide the theoretical groundwork that is needed to do that, to see the first implementation of device-independent QKD. This is challenging because, as we saw before, we need signals that are strongly entangled, and the relevant measure of entanglement is here the CHSH value. Something that I did not mention at all is the fact that, of course, if you want to perform the protocol that I've shown before, you need to account for the finite size effect, the fact that you cannot simply run the experiment forever. The statistics is finite, and then you get a prize from these finite statistics. And it turns out that this prize is quite large, meaning that you need, in addition to a very strongly entangled signal, you also need to be able to produce many signal pairs. All right? So we are considering an approach where the repetition rate is potentially very high, so that it might not be a problem to get many signal pairs. And this setup uses optical component. It's the red star is here a source that produces entangled photon pair in polarization, and we are here using a standard polarization measurement. So the question is, would it be possible to use this setup, which has been used already to perform Bell test, even in a very clean way without any loophole, to perform a first proof of principle demonstration of device-independent QKD, given that, again, in this scheme, the repetition rate is high and might not be a problem to get many signals here. The main problem here is twofold. The first problem is the loss. you get a chance that once the photons are produced, they get lost either in the transmission line from the source to the detector, or simply not detected by the detector. This is the first problem. And the second problem comes from the statistics of the source. These sources are based on spontaneous parametric down conversion, and they do not produce the maximally entangled state that you would like to get high CHSH quantity. But they also produce vacuum and multi-photon component, which strongly reduce the CHSH score, even in the ideal case where everything else is perfect, okay, due to this vacuum component and this multiple events. So what I'd like to show you are results that we got recently, where we showed that by adding noise to the row key, you can reduce the requirement on the global detection efficiency. And secondly, I also would like to show you quite quickly that if you now try to bound Eve information with a Bell inequality that is not the standard CHSH inequality, but which is a slight generalization of this inequality, you can bound a bit more tightly Eve information and get higher key rate in this same setup. So let's start with the noisification. So it's a trick that has been proposed some time ago by Renato Renner, Barbara Krauss, and Nicolas that essentially consists in adding noise to the reference key before the classical post-processing. So you might say it's not a good idea, because if Bob starts to add noise to the reference key, then this will reduce the correlation between E's key and Alice's key, and this won't help. But of course, you also have to account for the fact that this will also reduce the correlation with Eve. And the question is, does it help at the end of the day? And it was shown to help in standard QKD. You can basically tolerate more noise, quantified in terms of Q-bar, in a standard BB84 protocol, for example. And what we have shown here is that this also helps in device-independent QKD. And in particular, if you remember the lower bound on Bob's entropy with respect to Eve, we now have an additional term that depends on P, the quantity of noise that you add before doing the post-processing steps. This is the result. So here is the black line is the asymptotic key rate as a function of the overall detection efficiency, including all the loss from the source to the detector in the setup I've shown you before. And you see that there's a minimum threshold efficiency around 93%. It's very demanding in practice. No one can do that so far. Now, if you use a trick that was proposed by Ma and Mutkanau some time ago, where instead of using the Q-bar to estimate the cost of error correction, you really keep all the measurement results, then you get a slightly better threshold, a bit above 90%. And now, if on the top of this you also add the noisification, now you see that the requirement on the detection efficiency goes down to a bit less than 83%. These start to be much more reasonable in practice. Okay, so there's a hope that, you know, by adding noise, we can hopefully make a first proof of principle demonstration of device-independent QKD with optical setups. Now, I'd like to mention that somehow in currently available security proof, Eve information is bounded from the CHSH score only. And, you know, it's a bit annoying, because in practice, to get the CHSH score, you need to compute, or you need to get access to a correlation function. And then somehow you don't use the knowledge of this individual correlation function. You just compute, you know, a polynomial of this statistics, and only use this specific polynomial. So there is a question in the community asking whether we could try to bound in information in a better way by using the wall statistics. This does not take much in practice because you already have access to that. It turns out that in theory, we don't yet know how to deal with these statistics. We only have security proof using the CHSH core. And then instead of taking the wall statistics, we just took somehow the most simple generalization of the CHSH inequality, where we now add a parameter to 2 of the 4 correlators associated to the CHSH inequality. And now, given statistics, you can optimize this parameter. And in the setup I've shown you before, this is the raw result. The blue line is the line that I've shown you before. It's now a linear scale. Sorry for this. It could have been a log scale as before. So this is the key rate as a function of the detection efficiency, given that I'm dealing with an SPDC source, polarization entanglement, standard polarization measurement. And I'm using the trick of Milton-House for error correction and the noisy preprocessing. And now on the top of this are bound in information with the generalized CHSH inequality that I've shown you before. And what I get is the red curve here. So you see that this does not change the threshold, the minimum efficiency that is needed to get a positive key rate. But this basically changes the positively the key rates itself once you get access to high detection efficiency. Maybe if you can wait.
Is the bit per second?
This is the key rate. So it's the number of bit per try, say, right? That are probably secure.
Okay, so it's not per second.
It's per try, yes, per experimental run, yeah. Okay, so now, do we have time? 5 to 10 minutes. All right. So very quickly, so we just wanted to mention very preliminary result. We are arriving at an annoying point where somehow we will soon hopefully get a security proof from directly from the statistics, not from the CHSH core, but directly from the statistics. And now the question is, well, I have a lab, I have the possibility of dealing with several optical modes, of implementing several operations on these optical modes, like squeezing operation, displacement operation, and so on and so far, linear optical elements, and so on and so far. And the question is, what is exactly the setup that can produce the statistics that is the most favorable for me when I want to implement device-independent QKD? You cannot solve these things by yourself, and you need to use automatic search for this. And we made step along this line, and the idea there is we're focusing on a fairly simple experiment involving up to 5 optical modes. Each mode can be filled with up to 15 elementary operations involving, as I was saying, squeezer, displacement, phase shifter, beam splitter, and things like this. And we also have the possibility of using non-photon number resolving detector to get the final result, to get the statistics itself, but also to produce conditional events. And then we were using techniques using reinforcement learning to basically try to design an optical setup that produce the highest possible key rate, given that the main limitation is the efficiency. So we're using, at least so far, the first key rate that is only based on the CHSH value and includes the noisy preprocessing. And this is the reference line. This is the line corresponding to the standard polarization case we're discussing from 10 or 15 minutes now. And we succeeded to find fairly simple setups, only using 1 squeezing and 2 displacement operation to produce, slightly higher key rates. I mean, this is a log scale, so there's a significant improvement in key rate, and a slight improvement in the threshold regarding the requirement on the detection efficiency. So these are very preliminary results, but at least this shows that there's hope that even if I get a security proof that is based on the statistics, I can use automated search to basically design the experiment that leads to the most favorable statistics if I'm interested to implement device-independent QKD. All right, so with this, I'd like to conclude. I think the take-home message from the first part is that it might be useful to have a quantum memory, or to think about the quantum architecture where a small processor combined with a faithful and multi-mode memory. The question, of course, is how do you get to the point where the memory is extremely faithful and can really store a very large number of modes? Let me mention that multi-mode and faithful memory is not only useful for quantum computing, but it's known for some time now that it's also a very valuable resource for quantum networks, for quantum repeater, and then people are already thinking about that for, say, 10 years or maybe more. And we see step by step appearing a memory that can store, for example, 1,000 of mode with an efficiency of, not one, but close to 70, 80%, for example. So there are several motivations to try to think about ways to implement multimode and efficient quantum memories. The second part of my talk was on device-independent QKD. Our goal is to try to see appearing the first implementation of device-independent QKD. And I'll show you several tricks that can be used to hopefully facilitate the implementation of device-independent QKD. We're now reaching the point where we would like to get a security proof that, only, exploit all the measurement statistics and not a simple combination of them, and also to use machine learning techniques to basically design the circuit that leads to this spatial statistics. All right, with this, I'm at the end. Let me tell you quickly that the first part of my talk have been done essentially by my collaborator, Elie Gouzien. The second part on device-independent QKD was mainly done by Jean-Daniel Bancal and Pavel Zekatsky. Xavier Valcas, my PhD student, and Melvin Au they were also involved. And all this work has been done in collaboration with the group of Renato Renner at IPhT Zurich, Renato himself, and his PhD student, Ernest Tan. So thank you very much for your attention.